To be here. It's a special treat for me. I was an undergraduate and graduate student at the University of Chicago, and even almost the day I arrived, I knew about Ugo Fano because my father was a radiological physicist at Argonne National Lab, and actually Fano had consulted with that group. So he was a hero even when I was in college. I think he was a hero to all of us at the University of Chicago. Not only because he was such a great physicist, but he was such a direct link to Fermi, who had passed away only 9 years or so, 10 years before. I remember him regaling us with stories of Fermi trying to make pentodes in the lab in Rome and failing miserably, which gave us a lot of courage, those of us who wanted to be experimentalists. The thing I want to tell you about today are what I like to call artificial atoms and some of the behavior that they manifest. And the work that I'm going to be talking about is primarily the thesis research and other research of David Goldhaber-Gordon, who is now at Stanford, and Jörn Gerres, who has gone back to Germany. First of all, I'll try to convince you that this idea of an artificial atom is a useful one. When we confine electrons in small regions of space inside metals or semiconductors, the charge becomes quantized and the energy becomes quantized, and in that respect, these systems behave like artificial atoms. But the connection, the analogy is really much deeper, and this we found about 4 years ago after 10 years of theoretical work led by Ned Wingreen and Yigal Meir. We found the Kondo effect, which they had predicted, which is, as you've heard already, a property of magnetic impurities either in metals or on surfaces of metals. And in these single electron transistors, which we make, we're actually able to control the parameters in this Kondo problem very nicely. And as a consequence, when we actually begin to delocalize the electrons, we start to see Fano line shapes, and that's hopefully the major thing that I'll discuss. So let me tell you how we make these things. So the simplest way you can make a single electron transistor is by just putting three pieces of metal together with tunnel junctions in between. If you had a big piece of metal, I guess this is oh, I see. Okay, good. Perfect. So if you had a very large piece of metal in the center, there would be nothing to inhibit the electrons from tunneling stepwise from one end to the other. But when the metal particle in the center becomes very small, a gap opens up for tunneling, and this is simply because it takes energy to localize the electron on the central particle. It takes an energy E squared over 2c to charge up the capacitance between this particle and all the other electrodes. C is the capacitance. It would take E squared over 2c to add an electron, E squared over 2c to remove an electron, and therefore there's a gap of E squared over c, this U that we heard about, this charging energy, for adding an electron. And therefore the is this better? And therefore the number of electrons on this particle becomes quantized. It becomes quantized by isolating it between these tunnel junctions, and no current can flow. However, you can overcome that that barrier for current to flow by attaching another electrode nearby with no tunneling, an electrode which just changes the electrostatic electrochemical potential of this metal particle relative to the leads. You can think of it as just lowering the electrical potential, and then electrons want to hop on, so when you overcome the tunneling barrier, you reach a point where the number of electrons becomes uncertain. The number of electrons fluctuates between n and n plus 1. And if you raise the voltage on the gate a little bit more, you'll then quantize the number at n plus 1. And then if you go further, you'll see fluctuations between n plus 1 and n plus 2. And as a consequence, you get a series of conductance peaks, which I'll show you in a moment. First, let me tell you actually how we really make these things. We don't do it with metal particles, although people do. We do it with gallium arsenide heterostructures. By the way, we used to say years ago that gallium arsenide was the material of the future, and it always would be. And that was a joke because nobody ever made anything useful out of it. But it turns out that now in your cellular telephones, the front-end amplifier always has a gallium arsenide transistor in it. The way these things are made is you have a piece of gallium arsenide and an insulator of aluminum gallium arsenide on top of it. The insulator is doped with silicon so that it has extra electrons which fall into the gallium arsenide because their energy is lower there. And then if you attach a gate electrode, if you apply a negative voltage to the gate, you can repel the electrons and they leave, and you turn the transistor off. If you make the gate electrode positive, you turn the transistor on. For the transistors in your PC, it takes about 1,000 electrons to go from the off state to the on state. But in the transistors we make, it takes only 1 electron. The way you do this is like this. This is the same kind of structure. There's gallium arsenide underneath. Aluminum gallium arsenide is the insulator. That's this purple stuff. You have source and drain contacts to get the electrons in and out. And then we fashion very small electrodes. I'll show you a picture later on. Typically hundreds of nanometers or thousands of angstroms in size. And we fashion them like this. So there's 1 electrode on this side and 2 on this side. And when we apply negative voltages on them, they repel all the electrons out of the region in here. You still have electrons in the ends for the source and drain. And then you get a confined droplet of electrons in the middle. And then the middle electrode acts as the gate. And by changing its voltage, you can change the number. Change the number of electrons in the droplet. So just to make it a little bit more specific, when you put these electrodes on the surface, you create an electrostatic potential for the electrons that looks like this. And the electrons get confined in the middle. There are electrons on each end. But to get through, they have to tunnel through these potential barriers. So when you make a device like that and you change the gate voltage, instead of the conductance through the transistor just turning on once when you add electrons, now the conductance turns on and off and on and off over and over again. And by just calculating the capacitance, you can show that the voltage between 2 peaks or the voltage between 2 valleys is exactly that necessary to add 1 electron to this droplet. So this is a transistor which really turns on and off every time you add an electron to it. It's an electron counter. What's happening, as I said before, is that whenever the number of electrons changes, then conduction can take place. So you have a metal, whenever the number of electrons fluctuates between 1 and 2 or 2 and 3, but in between you get insulators. So this is really a succession of metal insulator transitions as a function of gate voltage. This quantization of charge is actually a little bit mysterious. We usually think of the charge of the electron as always quantized. But if you put an electron in a block of aluminum, if you put electrons in aluminum, you can never tell where they are. So you can never say in any volume of space how many electrons are there. But once you insulate a region of metal, then you can count the number of electrons. And the condition is very simple. If the charge lives in the confined region long enough to feel the Coulomb interaction that's necessary to charge it up, then the number will be quantized. So that says that Planck's constant over the RC time constant to tunnel out of the confined region must be less than the Coulomb interaction. The Coulomb interaction, remember, is E squared over C. If you put that together with this, the C cancels out, and you get the condition that R is greater than H over E squared. H over E squared is the quantum of conductance. It's the unit that comes into the quantum Hall effect. It's the unit that comes into all microscopic theories of conductance. And this shows you that it's also the quantity which tells you whether electrons are localized or delocalized. So whenever they're localized, then they become quantized. And one of the things that Ned Wingreen taught me was the condition for charge quantization is exactly the same as the condition for energy quantization. So creating a resistance around a region that's greater than h over e squared also quantizes the energy levels inside that region. And that means that we really have to think of an energy gap of U for adding an extra electron, but then there's going to be an excitation energy, some delta E, for exciting the system at fixed number of electrons. And so we really have something that starts to look like an atom with a level spacing for excitation and an energy for adding extra electrons. And we can study that excitation spectrum by now applying a source drain voltage. So I talked with these sharp peaks. We had an infinitesimal voltage between the source and drain. We were really trying to find out when we could get current to flow at infinitesimal voltage. But now we can apply a larger voltage, and when we reach the threshold for adding charge, current will begin to flow. But then when we can excite can access an excited state as well as the first state for adding electrons, then more current will flow. And so if we then differentiate the current as a function of this source drain voltage, we should see peaks for every one of the excited states of the artificial atom. Of course, we'll see a big peak when we first get to the point where we can add charge in the first place. So a good quantity to look at is the derivative of the current with respect to source drain voltage. And we can plot that as a function of both gate voltage and source drain voltage. And here's the most beautiful experiment that I know of this kind. This was done by Cohenhoven's group on single electron transistors made by Terucha at NTT in Japan. So let me take you through this a little bit. If you go along this axis of zero source drain voltage, you see a series of peaks. The bright red are high conductance points. And these correspond to the peaks that I showed you before at zero source drain voltage. But if you now, for example, are in this region where no current is flowing and you increase the source drain voltage, you get to a point where you begin to see current flowing because you're able to change the number of electrons. But then you see a series of additional peaks, and those correspond to the excited states of the artificial atom. So these are excited states with an extra electron. These are excited states with an extra hole. And in principle, you can map out the level spectrum of the artificial atom by looking at all of these things. Now, when we first started doing these experiments, and I suggested this name artificial atom, I talked to Dan Kleppner about it. Of course, at MIT, whenever you want to have a name for something, you have to consult Dan. And he looked at the data and he said, well, you may have made atoms, but you made very bad ones. And the reason was that our devices had very low symmetry, so orbital angular momentum was not a good quantum number. But these guys have made artificial atoms which are very circular. And as a consequence, you begin to see the shell structure associated with the angular momentum quantization. And that's why you see these magic numbers of 2, 6, and 12. These are the filling of the orbital degeneracies for a two-dimensional harmonic oscillator. They also see effects of Hund's rule and so on. So we really have gotten to the stage where we can really make things that behave in many ways like atoms. So then let's go one step further and think about making, as I showed you, these level spacings can be big enough so you start to see shell structure. So let's imagine making the artificial atom small enough so that the level spacing is actually bigger than the charging energy. In principle, that's possible. And then you would have a level spectrum that looks like this. If you added the nth electron here, then if you wanted to add another electron, you would have to add only the charging energy because you are adding the electron to the same orbital. But if you want to add a third electron, then you have to go to the next orbital, and that costs an extra energy delta epsilon. So what we're going to do now is focus on a single one of these orbitals and just the filling with 1 or 2 electrons. And what the theorists had been telling us actually for a decade, that in these artificial atoms, something very interesting would happen if you considered this situation. If the coupling between the localized states in the artificial atom and the leads was strong enough. So there's another energy in the problem. We've already talked about two, the charging energy and the level spacing. The other energy is this gamma, and this has been raised in the context of the Fano interference already. Gamma is the lifetime of one of these levels of the artificial atom. That is, if you put an electron into one of these states and you ask, how long it takes for the electron to tunnel out, that time will be h over gamma. So gamma is related by Fermi's golden rule to some hopping matrix element and the density of states in the leads. So each of these sharp levels that I've drawn acquires a width of gamma. And if the Fermi level is here, then several of these bands are filled, and then there's one that's empty. What the theorists told us was that under these circumstances, something new would happen if there was an odd number of electrons on the artificial atom. So if we have an odd number of electrons, then we have this level filled and this level empty. Now we've labeled this level as epsilon 0 below the Fermi energy, and here's the next, the energy to add the next electron is at epsilon 0 plus u. But now what the theorists say is that there's a new peak that occurs exactly at the Fermi level, a peak in the density of states, and this is the Kondo feature. It comes about because there's a kind of weak chemical bond that forms between the unpaired electron in the artificial atom and the electrons in the leads. The same thing will happens, as Ned will describe, when you put a transition metal atom on the surface of a good metal or inside a good metal. And this problem, so this weak chemical bond is so weak that it shows up only at the Fermi energy. And the strength of that bond is measured by the width of this peak. By the way, this Kondo problem is one of the truly great problems in physics. It was discovered in the 1930s in the resistance of metals. It wasn't until the Anderson Hamiltonian that people could even begin to approach it quantitatively, and it wasn't actually solved until Ken Wilson invented the renormalization group theory. It's a really great problem, and the measurement of a great problem in physics is the number of physicists who ruin their careers working on it. And in this case, by that measure, it's a truly great problem. So if you have this, I mention that because it's really exciting to me that we can actually study this Kondo effect now in a new way. So if you have this peak in the density of states, of course, that peak is associated with coupling to the left lead, but there's also, you can think of another peak associated with coupling to the right lead, and only when these two peaks line up will you get this extra conductance from it. And so you expect a peak in the conductance only when the source drain voltage is essentially zero, only at zero bias. And sure enough, when we do that experiment under the right conditions, we see these pretty results. So here, now you see these broad features. These correspond to the diamonds that you saw in the Cohenhoven experiment. They're very broad now because we've increased the coupling to the leads. That means we made gamma large. And if gamma is large, then the spread of voltages over which we see this charging peak is very large. But now you see this new feature, very sharp, right at zero bias, corresponding to the Kondo effect. And it's not there when the number is even, but it is there when the number is odd. And then just to convince yourself that it really has to do with the spin, you apply a magnetic field, and you see that the peak splits into two peaks, one for spin up and one for spin down. And there are many, many interesting things I could tell you about this Kondo effect, which I don't have time to, but let me just say that we were able to actually test the theory in ways that have never been before possible because we have such control. I'm a little embarrassed by the next view graph, but I will show it anyway. So this is the only time you'll ever see a micrograph with creation and annihilation operators on it. So this is an actual micrograph of the kind of device we use. This bar is 1,000 angstroms, so we're really making, because of the fringing fields around the electrodes, the electrons are confined to a region of about that size. So we're really made a droplet of electrons, which is about 1,000 angstroms in diameter. The electrons are out here in the leads, and they can tunnel through these constrictions into the droplet. And here is the gate. We confine the electrons with these three electrodes, and then adjust the voltage with the gate. So you can see what's happening is that if we change the confinement, we change the voltage on these electrodes, we're affecting gamma, the tunneling between the artificial atom and the leads. If we change the voltage on the gate, we're changing the depth of this energy level of the artificial atom relative to the leads. So in a sense, we really have here control over many of the terms in the Anderson-Hamiltonian. There's the T term, which we control through this. There's the epsilon 0 term, which we control here. These are the energies of the states in the leads, which we don't control. The charging energy is varied somewhat by changing these electrode voltages also. But the important thing is we can measure all these parameters. We can measure epsilon 0 and T and U. And so we can characterize the Hamiltonian that describes this electronic device. This is really an amazing thing, that you have an electronic device and you can turn the knobs and change the parameters in a many-body Hamiltonian, and it just works. So obviously, as we've heard, that's the Hamiltonian that contains the Fano physics. So it should be that if we increase the gate voltages, the coupling enough, then we should start to see Fano line shapes, and sure enough, we do. So here you've seen this before already. So this is the limit when the constrictions are very close, the coupling is very weak, and we see these sharp single electron charging peaks. When we increase the coupling, we first see Kondo effect. Kondo effect corresponds to increased conductance when the number of electrons is odd. That's this sharp peak that I showed you before, and that fills in the region between the two Coulomb charging peaks. So we get pairs of peaks here, and then when the number is even, we don't see the conductance. And then when we increase the coupling even more, we start to see these Fano line shapes very nicely fit by the Fano form. Yes?
You're implying the Kondo will not come from the Fano theory. I mean, it's not an additional source. It's really a separate physical thing.
You need the U to get Kondo effect, right? Because you need... Anderson invented this Hamiltonian in order to keep...
Yeah, but is the U a source term in a Fano theory? That's what I'm kind of asking myself.
Not in Fano, as far as I know.
I don't care if he put it in, but could it be put in as a source? That's what I'm... Or is it's really...
I think these things are independent. I mean, I think that you can... If you have a U term, then you can quantize the number of electrons in the localized state. But I don't think you need that to get Fano.
Excuse me. Why are the peak heights different?
Pardon? Oh, why are the peaks height different? This is another lecture. So it turns out this is a manifestation of quantum chaos. It's because the electrons are confined in an irregular geometry, and each wave function is different. And so as you add electrons, you're getting different wave functions which each couple differently to the leads.
I have another question. In this, we don't see too much a variation of the density of states, right? Shouldn't you see that also?
I mean, this is a huge variation in density of states.
Oh, this is purely density of
Well,
states?
you can think of it that way,
okay.
right?
Well, you know the J term after the width, which is the density of states, right?
I mean, the point is that what you're seeing here is a line shape which at high temperatures would be a Lorentzian, right? Which gives you the density of states for the localized state coupled to the continuum.
I'm talking about the density of states outside.
Oh, outside. The density of states outside is varying very slowly on this scale.
Okay, but if it was not, you would see it.
Oh, yes. But the density of state, this voltage scale here, to convert it to an energy scale, you need to know all the capacitances in the problem. And it turns out that that's a factor of something like 15. So we're really talking about in energies here something on the order of millielectron volts.
So you consider the density of
the density of
purely
states
parabolic in this case?
Oh no, it's constant because it's a two-dimensional electron gas.
Okay.
Right.
Okay.
So it's a very, very good approximation. It's not varying. Okay, so we know that if so the question is. And this is not something we've completely resolved, but we assume that there is some non-resonant channel for tunneling directly through the artificial atom, and a resonant channel which uses one of these charging states. And of course, the resonant channel has this pi phase shift as we go through it, and the non-resonant channel will have a weak phase dependence, and that's what gives rise to the Fano interference. 5 minutes, good. I don't need to repeat this except to point out that an interesting thing happens to the Fano form when when you let Q get very large, you want to approach a Lorentzian. But if you let Q get very large, this whole thing gets large. So G0 has to go to 0 in such a way that in the limit that Q goes to infinity, the product goes to a constant. Otherwise, you don't get the Lorentzian line shape. So that will be important for what we do next. So again, we're making artificial atoms. Natural atoms have Fano line shapes. We should see Fano line shapes, and we do. The nice thing about the artificial atoms is that we have this control over the parameters in the Hamiltonian. And in particular, what we can do here is change the coupling through the left constriction or the right constriction independently by just changing the voltages on these different electrodes. So in this case, we opened up the left constriction, and we went from a Fano line shape with Q very close to 0 to one with a very large Q. In this case, when we changed the right constriction, not much happened to Q. There's some broadening in the line. And that actually makes a lot of sense. When you have two constrictions in series, the one which is more opaque limits the height of the transmission, and the one which is less opaque limits the width. So the one which is more opaque is going to limit the coupling to the localized state, and that's going to limit the determine Q. The other one's going to just change the width, and so that's what happens over here. If we then fit all these peaks to the Fano form, we had to assume some incoherent background. And if we did that, then the important thing I wanted to focus on are these blue curves. So here's what Q is doing as a function of this voltage on the left constriction electrode. And then G0 goes to 0 as Q goes to infinity, because they have to compensate each other. In the other case, Q changes a little bit, but the biggest thing is that there's just a change in gamma. So this is really remarkable that you can get in and with the knobs really change the terms in the Fano form. Let me just finish up. I'm sure I'm out of time. Here are some other peaks we found where the Q was really quite small, and then we measured the differential conductance associated with these as a function of drain voltage and source drain voltage, just like the diamonds I showed you before. And we see beautiful diamonds again. But shockingly, these are diamonds in negative. These are negative diamonds. So there's high conductance everywhere except at these black lines. So these are anti-Coulomb, anti-blockade. These look just like our Coulomb peaks, except they're suppressions of the conductance. This is really remarkable. I don't think we really understand all of this yet. So let me stop there, and I'll take any questions you have. I just wanted to summarize. When we confine electrons with resistances around them greater than E squared over H over E squared, that should be, they behave like artificial atoms. That is, their energy and charge are quantized. We can control the coupling to the leads, and the first thing we see is this new Kondo state emerging. And then as we approach the deconfinement, as we really start to open things up, then we start to see channels which can go right through the artificial atom from one lead to the other, interfering with resonances on the artificial atom, and that gives us the Fano interference. I apologize for that one. Okay, thank you.